So this is dependent because it is zero. Because I said if it is zero, then it's dependent. What does that mean? Basically, it means that one equation is like this if it's dependent, like you can cross each other. And if it's independent, it means that you can never go like that, even if you do a plus or minus c. Why is that important? Well, you need two solutions for an ODE that is second order. A second order needs two solutions, and they have to be independent of each other. Otherwise, we go into a problem of them not being independent. And if they're not independent, then they can't be the two independent solutions to that ODE. It is just one dependent solution, one independent solution. So we start off by showing that cosine and sine are independent, and it makes sense if you think about it because cosine overlaps like this, right? If I remember correctly. And no matter how much plus c you do, these will not collide to each other. Um, why is this important? It's for variation of parameters. Honestly, that's the only reason I've ever used this and ever will, because I have numerical analysis to do that now, so I never will touch this ever again, unless I need like a really specific solution, probably researching more. Um, Yes. So Abel's identity is next, and second order, I derive it. Here's the derivation. It's very simple. You just take the Wronskian because this is a scalar. You can take a product derivative, which will give you this, because the original one was, if I go back over here, the original was this basically over here, as you can see. So I take a product rule again of these two, which means just spread it out, which will allow us to get this format over here. After you get this format, you realize that these two cancel out, leaving us with an even interesting equation. Now we get the second order differential equation. We can always turn to this form if it's homogeneous, which allows us to get this form over here. So I did it here. But over here you get this in the end, which if you simplify it more, you realize if you move out the p out, you get the Wolfskian again, which tells you that this is true for a second order equation. So with that second order equation, you can solve it because it's a first order differential equation. So imagine this just being x and x, and then solving that like any first order differential equation you ever solve. Therefore, you get this the Apple's identity for second order. The general one needs a trace and everything. I might do it. It's just a pain in the ass to do it. It's a lot of summation and index notation that's a little bit painful. I might do it. I'll think.